right. So, what is data mining? We have talked about data science, talked about data analytics. This is supposed to be an earlier lecture before this lecture was supposed to come up um, before data visualization, databases, and all that. But I had to just put up all those other lectures and then treat this one now. So um, basically, we have some interesting things to talk about here. So it's better I had to just really leave this one for a live class so that we can talk about this. I'm sure you must have heard this term before, data mining. It's first of all, it's one of the earliest terms in the data space, even before we had terms like data science um, and data analytics. So we have this more or less this area of data, this field that has been in place for some 20, 25, 30 years now. So if you've heard about this, I would like to know what comes to mind when you hear the term data mining?
Uh, to
Yeah.
me, simply put, data mining is just collecting information from a large set, maybe not, might not
Are you sure the
necessarily
call
be
has
a
finished?
large set, but like from a set of data, getting
Okay.
specific
That's how the call goes.
information, what is needed.
Sorry, I think I lost you at a point.
Hello, can you hear me now?
I can hear you now.
Okay, I said in like simply put, maybe in simpler terms, not the technical term maybe, but to me data mining is just like collecting specific or pertinent information from a set of data that is available. Like mining is getting things
Extracting.
that we need from raw, exactly,
Yeah.
extracting from large set of data.
Okay, great. Okay, Ken, how about you? What do you think about data mining?
I think it's just the same thing, like trying to get lots from what you have available.
Okay.
So you just try to bring out, extract from the available information or whatever data you have.
Okay, that's a good one. So yeah, we have pretty much said it, and now what we'll be doing is look at in more detail the very broad meaning of data mining, and let's go into more detail. Now, first of all, data mining is interdisciplinary, which means just like data science, data mining encompasses techniques, methodologies, best practices from different fields. So, data mining was what data science is trying to be today. Data science and data mining in those days, some 20, 30 years back, you know, what we call data science today, right? Back then, 20, 30 years ago, when a lot of work was not being done on data, back then we typically had, you know, people either working as statisticians or working as data mining professionals. And even as data mining professionals, they will still do a lot of statistics. And so data science has kind of evolved as a combination of all the processes and methodologies that were being used in data mining, in statistics, and in closely related areas. So data mining is interdisciplinary, even though it's emerged like or it has been on ground for some 20, 30 years ago. It doesn't really mean that it is already outdated, right? Because first of all, in various organizations today, we still have data mining teams. We still have processes being approached from data mining perspectives. We still have some methodologies, life cycles, processes that pretty much came from data mining, even though they have been adopted into the more modern and mainstream data science world, right? They are still recognized as data mining practices. And so data mining is still an active term today. Now, the goal of data mining is to automatically discover and extract unusual insights from large amounts of data. So, what data mining does is that we have a large data set or a large database or we have data, you know, um, data just really being so abundant somewhere online, somewhere on the internet. It could be on Twitter, it could be on social media, it could be over various digital media channels. And so we have these large amounts of data. What data mining tries to do is to, first of all, discover the insights. So it wants to go into that pool, that large pool, or should I say ocean of data, to first discover whether there are insights. Are there insights? Are there meaningful, valuable insights in this data? Are there valuable um, valuable things that we can discover that can really help us as a business to improve our processes, build better products for our customers, and at the same time improve business performance. You know, when that has been discovered, then the next process is to extract. Right? We'll really dive into this. I think in the next slide, we'll dive into the various processes in data mining. So first discover, and the discovery should be such that it doesn't have to be manual, which means a human doesn't need to be involved with maybe going to iteratively search for whether or not there are insights, trying to check different portions of the data. So we need to have a system, an automated system that would automatically discover those insights and retrieve them from the pool or the ocean of data. Then the output of a data mining process becomes input for further use. So pretty much data mining is not like an end in itself. Data mining is a means to an end. We implement data mining, particularly what we do mainstream now. Back then when data mining was all there was to working with data, data mining could be regarded as an end. So we have a full data mining workflow. But nowadays, right, that we have a more robust data science field and we have a lot more processes and activities to implement with data, right? When we are implementing data mining now, we utilize data mining as a means to an end. So where data mining stops, right, the results that the data mining process delivers to us is now what we are going to use for further activity like modeling, like prediction and decisions. Does it make sense?
Yes.
Okay.
Yes.
So with data mining now, we extract insights from the data. Of course, the insights we extract from the data is also data itself, right? And remember one of the things I talked about in one of our earliest classes when I said, um, you know, process data is information, and even the information itself is also more data. Can you guys remember that lesson? Where we
Yeah,
said that,
yeah.
yeah, where we
Yeah.
said that even the information you get from data is also data itself, right? Because it can be used again as input for further data activities. So the insights we get now, right, we are going to use that as new data now as an input for further use. So we could maybe we go through Twitter now. You already know that Twitter is a very big place. It's a world on its own. It's a universe of data, right? And we want to kind of figure out sentiment um, for 2023 elections. So let's say we want to be able to analyze sentiments among Nigerians on Twitter. Who they're interested in, what candidates they prefer, what are the things they're looking at in candidates, what parties, and things like that. So the first thing we do is, if we want to implement a data mining process, the first thing we do is discover whether one, we have Nigerians on the platform, and the answer is yes. So it would discover that here, the Nigerians on the platform. The second thing is that we want to discover whether Nigerians on the platform are already releasing their sentiments about the prospective election, whether Nigerians are already talking about it, whether Nigerians are already whether there are conversations around all this. So it will discover that. When it does discover that, the next process now is to implement various algorithms to extract, you know, um, the insights, but not just insights now, unusual insights, which means we're not just trying to extract the tweets that Nigerians are making about, okay, we prefer this candidate. This candidate has this specialties and all that. We're not really trying to recover those tweets in particular, right? We're trying to recover some unusual insights, like maybe connections and relationships between the various people tweeting those tweets, right? And use that to kind of map how we think that um, the ratio would be when it comes to user acceptance of these candidates, So we're not really going to be retrieving the tweets. So, but at the end of the day, what we are going to be getting as output from this data mining process is not necessarily going to be tweets and things like that. It's going to be it could be things like relationships between people making the tweets, right? Clusters of people, like people falling into similar categories, and things like that. So all those kind of information that show some uh, um, patterns that are not going to be so obvious immediately, some hidden patterns that are not immediately obvious to anybody on Twitter. That is what data mining tends to, or should I say, strives to retrieve. When we have retrieved those unusual insights, those intrinsic patterns from that data now, we now use that output as input for further process. So we could say, okay, let's now build a predictive model now based on these insights we generated from this procedure. Let's build a predictive model to determine, or should I say, to predict what candidates, what candidate stands the chance of winning the elections, right? It could be more than one candidate. Some candidates could stand the chance of winning the elections. Some could outrightly not even stand a chance. And of course, we have seen this in previous cases. There are some people that just come to mark, should I say, just to mark the attendance uh, that they that they declared candidacy and all that, But then we know that when it comes to elections, there are some obvious candidates that, yeah, they're going to be called, be on the top performing charts, and so we could predict the candidates that are likely to really top. Then after predicting that, we could now go further to really determine who the winner would likely be. So given top contenders for the position, right, this is likely going to be the winner. We could build models like that. Then we could also build decision models. Decision as to who do we really vote for based on this data. So sometimes we're not really trying to predict something. Sometimes we just really want to decide. And the human mind is a place of complexity. If we are Sometimes we can think about so many decision options and we might not know which one to go for. Why? Not because the brain cannot really decipher the logic and really determine what to do. The brain can do that, but many times our sentiments, our biases, and our emotions cloud our judgment. You understand? So instead of having to second guess what decision to take in the pool of decision options, we can then decide, okay, let's build a decision optimization model that optimizes all the options and picks out which one will produce the best outcome. Pick out the best decision that must be that if that decision is made, will produce the best outcome. So all these various activities, right, have been enabled by the data mining procedure. So many times when we are running all these things, we can do them without data mining. We can build predictive models, we can build decision optimization models without really going through a formal data mining procedure first. But in most cases nowadays, many data science project workflows, particularly for large scale data analysis and predictive analytics, most times we find that we have data mining being in the loop of those procedures. Does it make sense? All right. Now, this final point, data mining, um, is a misnomer. So it is extraction of knowledge, not data. Now, the thing is, when you look at this term data mining, the meaning, the literal meaning, right? If we have to just do direct translation, is we're trying to mine data. But from what I've explained so far, if you remember, I said if you dig into Twitter now and implement a data mining procedure, right? We are not really going to be extracting tweets. The tweets are the data. So what we are doing is that we're not going to be extracting tweets. We're going to be extracting insights from those tweets. So that tells you that it's not really the data we are mining. What we are mining is knowledge. What we are mining is insights. So yeah, it's like a misnaming, you know, even though the term is actually very sleek and nice compared to maybe using a term like knowledge mining. That's too long and maybe unattractive. But when you use the term data mining, and if you look at the history of data, of working with data, the history of industrial applications of data, business adoption of data processes, right? The data mining term, has really created a lot of buzz for organizations and enabled organizations to get a lot of investment, funding, and all that. Data mining, the term data mining also helped, academic researchers get research funds for, for research projects. So it was a kind of term that was attractive to investors, um, to funding organizations, grant organizations, and things like that. So it was a really nice term. But for the outside world, it's like, okay, you guys are trying to mine data, so they are attracted by. But as insiders now, you discover that what we're really doing is not that we're mining data, because data is everywhere. So we're not really trying to mine the data. It's everywhere. We are not trying to capture what is readily available. The data itself does not provide value. The value is not really in the data itself. The value is in what we can get out of that data, right? And so what we are going to be getting out of the data is knowledge. So the goal of data mining is to mine knowledge, right? Mine knowledge. Now, because of this kind of goal, right, there was a term that emerged called knowledge discovery in databases. I've called this KDD. We're going to look at that later. So we have KDD, knowledge discovery in databases. So it's like saying what we're really mining is knowledge. We're trying to discover knowledge, right? Although much later they would now get to realize that it's not just about discovering knowledge now, but also extracting that knowledge. Because discovering knowledge, well, we discover it, so we know that the knowledge is there, but how does that help us, right? So we have to be able to extract the knowledge, you know so in fact, earlier on, the term, when these procedures were being created, right, the term was just pretty much knowledge discovery in databases until it was just really adjusted, kind of branding, you know. So many of the things that we are doing in the data space, many of the terminologies we use are just pretty much a lot of branding to make the field attractive to others, or to make others get interested in the field, right? So, because when you come into the field, the truth is that it's a lot of technical procedure, technical things, and those technical things are typically not attractive to people outside. They're not really attractive to non-technical people. So, in order to have non-technical people comfortable, to make them comfortable with the technical procedures that we're doing, it's just really best for us to drop a lot of the technical lingo and use words that are kind of smooth, sleek, and easy to relate with. Does it make sense?
Yeah.
Okay, great. So let's move on now to data mining. This is a very long definition, uh, but would 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 dive into it anyways. So what I'll be doing is I'll break down this definition into the various categories so that it makes sense. So that at anytime, any day when you think about data mining, at the back of your palm, you just really remember what are the keywords, what are the key things that we're looking at, right? And with those key things that we're looking at, it helps you, even if you don't word the definition exactly like this, you'll be able to make a case about data mining that actually makes valid sense. So data mining is a process of exploring data repositories. So number one, exploring data repositories, like maybe databases, um, data warehouses, anywhere there's data, right? Any store of data, whether it's social media like Twitter and things like that, whether it's digital media platforms like YouTube, media streaming platforms like YouTube, Vimeo, Spotify, any of those environments are pretty much data repositories, or whether it's even your local storage, your what's it called, your database, your local database, whether it's company database, whether it's on the cloud or on the premises, wherever the data lies, as long as it's a data store, we are going to explore that. So exploring data repositories to identify patterns and correlations in data. Why? With the objective of establishing previously unknown relationships and extracting information that can be transformed into a comprehensible structure for further use. Let's break it down. So I've I highlighted these keywords. So I hope you guys can see it. Explore, identify, establish, extract, transform, and use. Can you guys see the highlighted terms?
Yeah.
Yes, I can.
Okay, so now the long definition now, we can now make some sense out of it using these keywords. So the first thing we want to do is explore, right? What are we exploring? We're exploring data repositories. The next thing we want to do is identify. What are we identifying? We're identifying patterns in the data that we find in these repositories. We're trying to identify correlations. Now, what we want to do is that by identifying these patterns, now we want to be able to start drawing some inference. We want to be able to establish relationships that we did not know before, relationships that were not really obvious. I mean, think about the example I gave about analyzing sentiment on Twitter for the prospective election. And so we want to, first of all, when we dig into Twitter now, we want to be able to identify some patterns in the data. So what is the data now? The data is, the abundance of tweets that we have on Twitter, particularly tweets within Nigerian Twitter. And so um, any tweet talking about elections, political candidates, right? We focus on those ones. Now, when we focus on those tweets, now we want to identify some patterns and correlations within those tweets. The purpose of this is to establish previously unknown relationships. So typically before we began this procedure, we did not really know some relationships between the various people tweeting and all that, right? We're not aware of the similarities. We don't even know all of the users that exist tweeting. We only know that people are talking about Peter Obi, people are talking about Tinubu, people are talking about Osibanjo, people are talking about Atiku, some of these candidates that are coming up and showing interest, right? So we have not really, yeah, we doing a lot of reading tweets and all that. We have been able to kind of make some sense about where people are kind of tilting to, right? We are already making sense about similarities between people preferring a particular candidate, you know. But then that's just really all there is. There's still some unknown relationships we cannot decipher just doing all those things manually. So we implement data mining to identify the patterns in order to establish relationships that we were not aware of previously. Right? What are the relationships between these various users tweeting about these candidates? Right? Are there some striking similarities? Are there some dissimilarities and disassociations? Are there some groupings and aggregations? Are there things that put some of these people tweeting in common? Are there common grounds for these guys? Even if they prefer different candidates, is there a common ground in their reasoning, in their thought process, and things like that? So typically, we analyze the language they are speaking, the words they are using, the tone in the language, right? Because this kind of data is not really structured data. It's not tabular data in tables. It's like unstructured. It's words, it's text, textual information. So, we would implement a lot of natural language processing techniques to be able to understand the tone in their communication, to be able to understand the sentiment and all that, so that we can now really understand what are the relationships we can establish them. When we are done establishing, okay, these guys relate to these guys, there's a similarity between users like this, so people who tweet like this kind of fall into this category and all that, then we extract valuable, useful information from what we have been able to establish. Now, when I extract information, when I begin to make inferences, right, which can now be transformed into a very suitable structure. Now, we can even now create a table, a tabular data now. So instead of having tweets as our final data, like tweets, which is just a bunch of words and unstructured data, we can end this process with tabular data now that we can now analyze with even something as simple as Excel. We can now use Excel to analyze it. You will not be able to use Excel to analyze tweets because Excel works with tabular data. And since tweets are unstructured data, they are textual information, you know, you won't be able to do that. So, but when you work with data mining, right, since it's not the tweets we are mining, right, we're trying to establish some relationships in order to now extract some information. Now, this information cannot be structured and put in a kind of um, tabular structure. If that's what we want, we could send the information to a database. We could just organize it the way we want it so that we can now use it further. So after this procedure now, we can now begin to do something like machine learning to analyze, I mean to to build a model based on that data, the final data that we got from this procedure, we just pretty much are able to now use this information. Typically, the tweets themselves, right? We may not be able to create models directly from those tweets, because they don't really make sense exactly the way they are. We have to really process them, and data mining is usually a very fast and automatic way of processing those information and ending up with actual valuable information that we can really use. Does it make sense?
Yes,
Okay.
I'm following.
Yeah.
Okay, great. So whenever you think of the term data mining, first of all, remember that what we're really trying to do, we want to dig into databases and then we want to be able to discover knowledge and extract that knowledge. So the first step is, of course, to explore. We want to explore. To explore means, to kind of scan through. We just want to scan through the database or data repository. So the first step is to explore. But when we are exploring now, we now begin to identify patterns and all that. By the time we are done identifying, we can now use the insights from this identification to establish. When we have established relationships, we then extract the information that we have been able to decipher from that. When we extract that, we can then transform what we have extracted into a structure that we can then use. So explore, identify, establish, extract, transform, and use. Six processes. So if you just remember the six processes, that it starts with explore, then we go to identify, then we go to establish, then we go to extract, then we go to transform, and then we go to using it. Then you realize that data mining is not really so much of a long thing to grasp. Um, to
Okay,
grasp.
you know.
Okay, great. So I was saying that when you think about each of these six processes, you now realize that it's not going to be so much of a difficulty to grasp, right? Once you understand the six processes, the six keywords that's really um, that the data mining procedure draws on, then you'll be able to really make sense of what we do when we are running a data mining procedure. So now let's look at each of these steps one after the other. So I've done a further breaking down, classify them into data mining phases. So we already talked about the six procedures: explore, identify, establish, extract, transform, and use. So these six procedures can be broken down into three core phases of data mining. We have the knowledge discovery phase. Remember what I mentioned earlier about knowledge discovery in databases, that when data mining started, pretty much this was the way they called it. So what they called it until later they had to kind of rebrand it to the term data mining, right? I hope you guys can still remember this line here. So that's like phase one, knowledge discovery. And so the first three procedures, explore, identify, establish, is under knowledge discovery. We want to first explore the data store, the data repository. When we are exploring it, we're able to identify patterns and correlations. Then we're able to establish relationships, right? So all this we are doing is to discover knowledge. When we have established relationships now, we have already discovered the knowledge, so we will go to phase two, which is knowledge extraction, right? And in knowledge extraction now, we of course we go to extract, then we go to transform. So when we extract, we don't just extract. We want to be able to now convert what we have extracted to a structure now that can now be used for phase three, which is advanced analytics. So typically when we use the term advanced analytics, right, if you go back to the data analytics lecture, you realize that, okay, let me go back to it from here. So um, remember these three subsets. If you have not gone through the lecture, when you go through it now, you find that there are three subsets now. We have descriptive analytics, predictive analytics, and prescriptive analytics, right? And so typically the first subset of data analytics is descriptive, and it's what you typically know as data analysis. It's just data analysis. So when you're creating dashboards, when you're using Excel, SQL, or even Python to analyze data, to get to immediate information, maybe run simple statistics or do a kind of simple hypothesis testing to understand the data. It could be maybe your user base in the company. It could be trying to understand the market. It could be trying to do customer segmentation, right? All those things fall under descriptive analytics, which is known as data analysis. So, I mean, if you've been wondering whether there's a difference between data analysis and data analytics, yes, there's a difference. The difference is that data analysis is a subset of data analytics. It is this first subset. And so it's just the part of data analytics that is concerned with analyzing data to understand historical events. So just going into past data and trying to understand what happened, why it happened, what are the meaningful insights we can get from this, what are the correlations, are there some striking relationships, are there kind of groupings or segmentations within the data, is there a way we can understand the market based on the insights we are getting from this, right? So all that is typically what you call data analysis. The moment we step into predictive analytics and prescriptive analytics, we have now gone into advanced analytics. So typically what your data mining tries to do is to kind of augment this first process so that we can now use the insights, the knowledge extracted now for these advanced stages, which is predictive and prescriptive analytics. So going back to this, we run all this now, extract the knowledge and transform it so that we can now use it for phase three, which is advanced analytics. So in advanced analytics, you would have things like prediction, decision making, and things like that. So if you look at this diagram here, we have various data mining techniques, right? And comparing these techniques now to these various phases, starting from exploring, identifying, and things like that, we typically would start from things like outlier detection. This is supposed to be outlier. So things like outlier detection, things like associations, and all that. Um, I don't think this diagram is not really ordered, right? It's not really ordered to follow the steps here. But many times the techniques are kind of iterative and back and forth. So we can implement things like outlier detection, association rule mining, clustering and things like that under knowledge discovery. So clustering, outlier detection, association rule mining will fall under phase one. Then for phase two, um, we we then extract, transform. Extract and transform doesn't really come into any of this because the other techniques the remaining techniques we have here are typically used in phase three, right? Although decision trees can still be utilized for phase two, which is knowledge extraction. But then for phase three now, when we want to now use the data that is to implement advanced analytics, we then begin to talk about regression, which allows us to predict, classification, which allows us to predict classes in the data. We can do things like decision trees, which allows us to build models that are trained on decision-making processes inherent within the data. So all these various techniques that you have in data mining, but the important thing to note here is that the various 6 processes now can be grouped into these 3 phases. So understand that the 3 core phases in data mining is knowledge discovery, then we have knowledge extraction, and then we have advanced analytics. It doesn't end yet. It's still pretty much interesting. If we start from phase 1, um, I don't know. I hope you guys are with me because it seems I'm just really engrossed in
Yeah, I'm
this
following.
topic.
Yeah, yeah, I'm
Yeah.
following.
Okay, great. So if there's any point where you are lost or you need to ask a question, just let me know. I'll still take questions.
Okay,
Yeah, I'll still take questions later, but I just really want to exhaust what I have here. Then we'll go into questions.
okay.
All right. Now for phase 1, which is knowledge discovery, we have the first step, explore. So typically we want to explore. So what do we do when we're exploring? We are scanning through the database or the data store. We're scanning through wherever the data is. We want to be able to um, we want to be able to scan. So we do a lot of searching. Since it's an automatic process, we can just build a search algorithm that will just search through the data. Then as it's searching through the data, it's running techniques you call EDA. So, are you guys familiar with the term EDA? Let me know if you know what EDA is. Have you
No, I
come across
don't.
this? Okay.
No.
All right. How about Olutomi?
No, no.
Okay, so EDA is short for exploratory data analysis. Right. I'm sure you must have heard that term before, exploratory data analysis. Um, we are pretty much trying to analyze data by exploring it. So exploratory data analysis. So we run exploratory data analysis processes in the explore phase. Of course, that makes sense because this is explore. So exploratory analysis, for example, some sort of visualization to understand the data. You know, we try to get some summary statistics. We try to get the distribution of the data. For example, we want to know whether the data is a normal distribution, whether it's even a continuous distribution, or whether it's a discrete distribution. We want to know what kind of continuous distribution. If it's continuous, what kind of continuous? Is it normal? Is it exponential? Is it Gaussian, or is it a gamma distribution? Then for but if it's a discrete distribution, we want to know whether it's a binomial distribution, a Poisson distribution, or um, or a geometric distribution, right? So exploratory data analysis allows us to check these things. We want to know the various fields in this data, what distributions do they follow, right? What is summary statistics? Is the distribution skewed, right? What is the skewness of the data? What is the kurtosis of the data? Is it heavy-tailed distribution? Is it light-tailed distribution? Is it a symmetric distribution? Is it an asymmetric distribution? So many questions in the EDA phase, all these questions being answered by the algorithm to decipher what really exists in this data, whether we really have what we need in this data. So we explore the data in the database to understand whether we have what we need. Once that step is done and we find that, okay, we pretty much have what we want in this particular database, we go to step 2 in phase 1, which is to identify. What are we identifying? We're identifying unknown patterns. Unknown patterns now could be clusters. So clusters, for example, when we use the term clusters in data science, we're talking about groupings in the data, right? We're talking about groupings in the data. So um, let's go back to Twitter example with for sentiment analysis. So we have people that have made various tweets in the data, right? If I'm going through Twitter now to look at people um, tweeting about maybe Peter Obi, for example, typically I could just search for, maybe I could just use a hashtag to search for a trend and then be going through the various tweets in that. I can now use my head knowledge to be able to kind of look at some similarities in the data, right? And kind of make some sense from that, but that will not be scalable. Number one, that's going to be very laborious for me because for me to even get enough information from that, I would have needed to spend a lot of time on this procedure. So instead of doing that, what I would instead do is I would implement a data mining procedure to just dig into the database, this time around to dig into Twitter, and not just Twitter now, to dig into Nigerian Twitter now, and then when it has explored to find that the data exists, the data that we need exists here, then we begin to identify what are the patterns. So let's check for clusters. Are there some similarities within the people posting? I mean talking about a certain candidate. So where do the Twitter users fall into when it comes to their election choices, right? So does this person, is there a group that favors Peter Obi? So let's identify a cluster for that. Is there a group of Twitter users that favor Atiku? Let's create a cluster for that. Is there a group that favors what's it called? Bola Tinubu? Let's create a cluster for that. So we just really create clusters for all these. And within the clusters kind of reveal information about the relationships between those users. It's not really giving us information about the tweets exactly, the exact tweet they posted, but about the underlying sense in those tweets. So it's trying to make meaning from those tweets to give us some correlations and patterns in the data, you know. So another thing we want to look at is anomalies. So are there people who are thinking something different entirely? Those guys will be called outliers. So someone could just come up and say, you know what, let's vote for my local government chairman. You know, when you think about it in terms of the political atmosphere of Nigeria and in terms of the candidates that we typically will look at as capable candidates, and candidates that we look at as what's it called, as people that are popular enough to really get a lot of public sentiment. When you think about that and you now look at what this person is talking about, the candidate is talking about, you know that this kind of data that you have is an outlier, which means it is outside the range of what really what we really consider as valuable insights, right? Despite being outside the range, it can still be very useful because anomalies themselves can still provide us some information about what we are trying to study. So it can kind of provide us insights into how certain people, how a smaller group of people think, whether their thinking deviates from others. Then we have deviations, which are not exactly like outliers, but deviations could be like sort of difference in line of thoughts, right? It may not really be outliers in terms of maybe talking about a candidate outside the range of candidates that we are typically considering, but the deviations could be in the sense of maybe you're talking about a candidate, but you're looking at something entirely different. Maybe bringing when we're talking about things like what a candidate wants to focus on, things like economic development, infrastructure development, security, and all that, right? Some A user could be talking about something entirely different, like maybe saying something like if Atiku Abubakar should come on board, you know, he should he should he should how would I put this now? It's kind of bring a Harvard Business School model to the Nigerian space. You know, that really is totally different from what others are talking about. It's a deviation entirely. Now, this person that made this tweet, he is not an outlier because he's talking about a candidate that, I mean, a kind of candidate that others are talking about, but he has deviated from the point. I don't know if it makes sense. So this is a type of anomaly. Are you guys with me?
Yes.
Okay, great.
Yes.
Then another type of anomalies is, are errors. So errors, some people could make tweets that they're trying to talk something, but then they've made a lot of, the errors could be a lot of maybe grammatical errors, concord errors, errors that make it maybe difficult or impossible to analyze the intent of that tweet. So what does this user intend to say? Sometimes typographical errors could really spoil or could really, some things as little as something as little as comma could really create a different meaning for what you're trying to say. So when a user has not really paid attention to the detail and then make some errors in things like things as little as the grammar and all that, that could create a problem for our algorithms to really understand what it's saying. So that would be considered as anomalies too. But sometimes even errors too could be um, I mean, sometimes even errors are things of interest when we're trying to um, identify patterns and correlations in the data. They could be also useful, right? They may not be useful in the exact sense of these other patterns like clusters, right? But we could still really use them for something. So not all errors or anomalies, are thrown away. Sometimes anomalies are useful in the data because some anomalies really help us get meaningful insight into the reality of things. We don't really have to have perfect data. We just really have to have data that represents how the real world behaves. Does it make sense? And since people make a lot of mistakes, it then means the data that we'll be getting will not always be perfect. So if you have to be true, if when working with data you're always throwing away anomalies in the data, it then means you're more or less looking for a perfect world, and the perfect world does not exist. So why should you want a data representing the real world? Why should you want that data to be perfect? So sometimes anomalies could make a lot of sense, and it's not every time we really overlook or discard anomalies. Sometimes we really consider them useful for our workflow. Then another thing you want to identify is correlations. So correlations could be things like the relationship between different users. Like, okay, um, this user that said this thing and this other user, what is their geographic locations? Are they in similar geographic locations? Are they within the same age bracket? Are there some kind of some demographic relationships between these guys? And things like that. So typically, we just really want to identify the strength of the relationships between these users, and that will pretty much help us to also understand this aspect of clusters here. It would help us really understand why certain groups of people think the way they do, and then for those that deviate from the general line of thought, why they deviated in the first place. So correlations could also be interpreted as dependency. So some correlations are actually dependencies. Some correlations are like, okay, this particular example really depends on this other one. So certain features like geographic location, right? Um, does the tweet, does this, the kind of tweet or the cluster of tweets that we have, do they depend on the location that people are coming from? For example, we see that typically people in geopolitical zones like the north would most likely, not every time or not generally, but most likely favor another candidate, right? People from southeast would most likely favor southeast candidates, right? Except if there's no Southeast candidate, then they pitch their tent somewhere else. But it's most likely they favor a Southeast candidate, except if that candidate has shown a track record of um, of non-performance, and the Southeastern people are totally outrightly against that candidate, then it's not likely. But in most cases, they will favor that candidate. Southwest do the same thing, South the same thing. So that tells you that there are certain dependencies that we can extract from all this information. So it kind of gives us an insight into what kind of people are favoring a particular candidate, whether they fall within the same geopolitical zone of that candidate. And whenever we find users that are outside the geopolitical zone of a candidate, but they are favoring that candidate, that's an interesting observation. That's an interesting insight too that could also be very useful for us. When we are done identifying all this, very interesting information, we then go to step 3 in phase 1, which is to establish, right? To establish. Now, what are we establishing? We want to establish relationships. We want to establish um, we want to establish associations. So we begin to run a lot of techniques like dependence modeling, like trying to see if a particular feature in data, a particular a particular case in the data depends on another case or another feature, right? We want to see how strong the dependence is. So how strong is the dependence of user sentiment with geographical location, the the geographical location where they find themselves, right? Their ethnic groups and things like that. We want to be able to understand association rules. So we want to be able to fetch the association rules. The way association rules work in data mining is it's actually a technical it's a technical methodology. What it does is that it wants to figure out if then patterns. When we talk about if then patterns in data mining, what we really mean is that there are certain relationships or associations in the data that are kind of um, not just dependent, but they're such that something must have happened for this one to have happened. So um, the occurrence of certain events in the data must be dependent on the fact that a particular thing has occurred before. So if this is the case, then this is going to be the case. So we want to find out which patterns in the data are if then patterns. We want to find out which patterns in the data are patterns like if a user is in Ogun State, then he will vote for this candidate. If a user is in Abuja, then he will vote for this candidate. We want to be able to see if there are such if then patterns, right? The moment we find counter examples to those patterns, then that is not really an if then pattern. For example, if we find that someone that comes from the Yoruba ethnic group is interested um, in an Igbo candidate or a northern candidate, and we know that this is not really a scarce situation. It's a very common case. Some people will be from the Yoruba ethnic groups and be favoring, candidates from other ethnic groups. So when we have a single counter example to that pattern, like one user from Ogun State favoring a northerner or an easterner, right? When we have that single counter example, we may look at it as an outlier, right? Sorry, as an outlier, that's this guy, you know, we could look at it as an outlier. But the moment we begin to have multiple persons and the ratio is becoming interestingly large, then we say, okay, this is not an outlier. So in that case, um, this pattern is not really an if-then pattern. So we cannot conclude that if a user comes from Ogun State, he would vote for a Yoruba candidate. If a user comes from Anambra or from Enugu or from Ebonyi, he would vote for a particular candidate. So once we begin to find multiple counter examples to something we suspected was an if-then pattern, all right, that pattern ceases to be an if then pattern. So basically, an if then pattern is a pattern that must be consistent throughout the data. Does it make sense?
Yeah.
Okay. Before I proceed, I would like someone to give me an example. Just give think of another example of an if then pattern. I've already talked about an if then pattern in sense of elections. You could see use elections for that, but the one I just talked about now is a pattern where if a user comes from a particular ethnic group, it would vote for a candidate from that ethnic group. If this pattern is consistent across the data, then it's a general pattern. But if we find that um, there's a lot of users from an ethnic group that will not vote from someone from the ethnic group, then we cannot call that an if-then pattern. So the goal is to be able to discover the patterns that are going to be consistent throughout the data when we are doing association rules. Data mining will try to now fetch out what if-then patterns are actually really truly consistent throughout the data. So I don't know if you guys can come up with an example. Let's look at maybe one or two examples.
Okay, I can say I'll wash the car if the weather is nice. So it means if the weather is nice, I'll have to wash the car.
Okay.
Yeah, right?
Okay, yeah, that's an if then it's an if then rule, but then you are the only person in this data. You understand? So we will
Okay,
not be
has
able
to
to.
be include other people.
Yeah, you would have to think
Okay,
about an
okay.
example where you have multiple parties in the data, so that we will now try to check if we can find counter examples to that and see whether that pattern is really an if then pattern or not.
Okay, let me think of one.
Yeah. Olutomi, how about you? Have you thought of any example?
So I don't really have any example in mind.
Okay. Don't worry, all these things just really take some getting used to. A time will come when you just begin to, you'll be able to smoothly reason about some of the information. So we can have, let me give you another example, right? We could look at maybe a university, and we go to the university's database and maybe take a particular course from that database, right? And then um, maybe what we're trying to do is to analyze people who perform well on a course or within a particular department. And so we could run a data mining procedure now, right? And in the data mining phase now, we may be looking at if then patterns. So we want to see people that pass this course, right? Are there some what's it called? The first thing before we get to association rules, now we want to do identification. So we look at are there some striking relationships? People who passed the course, do they have anything in common? Which means are there clusters, right? Are there correlations between various issues in the data? Um, are there outliers? That's people who they fail the course, but it's not really because the course should have been failed, but they are outliers. And of course, there are some courses too where passing the course is an outlier. Like, I mean, think about courses where to get a B or an A in some of these universities in Nigeria, to get a B or an A in those courses is like you're a wizard. You just imagine that. So at that moment, like you're an outlier because almost everybody passing the course is getting a D, and maybe we just have like 5 persons getting a C. Then you have gotten a B or an A, and it's just you. Or maximum, there are just two people who got a B, or one person got an A in the course. And it's like, yeah, this person is an outlier. So we want to find, okay, what are the outliers in this data? What are the relationships and things like that? Once we have identified that, we now begin to establish. Let's now establish some. Let's now be able to. I mean, to establish means to quantify. So I've identified some things, but we want to be able to quantify the information that we got. We want to be able to establish it and kind of quantify it, so that we can now make inferences with that. So we could decide. Let's run association rule techniques, right? So what would be the if-then patterns in this case? If-then patterns could be things like if users read, then if users not really because the university may not have been able to capture whether or not users are reading, or maybe the times when users are reading. So maybe we can look at something else like the university was able to capture students that went to the library. So we could look at patterns like if students go to the library, then they passed the course. You understand? Now, we want to know whether this is a consistent pattern in the data. So we'll begin to look at the data. Um, this person went to the library. Did they pass the course? No. Okay, maybe that's just an outlier. We now begin to check. We now realize that there are a lot of people who went to the library but still did not pass the course. So we discover that the relationship between going to the library and passing the course is not an if-then pattern. Does it make sense? Does it make sense?
Yeah. Yes.
Yeah. So that tells you that because assuming we have 100% of people who went to the library passed the course, then it is an if-then pattern, right? But now we have that maybe 30%, people who went to the library did not pass. If we just had maybe 1%, we can look at that 1% as an outlier. So maybe out of 100 students, one student that went to the library, that's out of 100 students that go to the library, right? 99 passed the course, only one failed. We could consider that as an outlier. So we can still sustain this as an if-then pattern. What we might just do instead, we might just now build a kind of, should I say, confidence interval and say if we get 99%, right? 99% success rate in our if-then pattern, then we go for that. So our confidence interval could be 99%. So if we have 99% of the data following the if-then pattern, then we can say it is consistent. So the goal of the knowledge discovery phase, that is of this established step in the knowledge discovery phase, the goal now when using association rules now is to be able to discover what we of all the patterns in the data, which of these patterns are consistently if-then patterns. So that kind of gives us an insight into causative relationships, which means when this kind of thing happened in the data, it led to this situation. Does it make sense? Okay, great. So those if-then patterns now tell us that these are kind of dependencies, like this occurrence in the data depends on something. It's predicated upon a particular activity, and we're able to decipher that. We can use criteria. That's when implementing this association rules technique. We can use criteria like support, like confidence. These are statistical techniques that kind of give us an indication of how much what's it called to accept when running these techniques. For example, we could say that okay, if we have 99% of if then part of what's it called, if we have 99% of the data following these if-then patterns, then we can say it's consistent. We can then say that the rest of the 1% is like maybe an outlier, right? But then if we're having just as something like 60%, that then shows that 40% of the people in the data don't follow this if-then pattern, and that's a problem. So we cannot really generalize from that kind of information because it is not, 40% is already so big, so we cannot call that pattern an if-then pattern. We cannot say that okay, 40% of people in the library didn't pass, and then we now conclude that if people went to the library, then they passed the course. We can't make that kind of conclusion because already from the data we have already seen that 40% of the people in the data did not pass the course. Does it make sense?
Yeah.
Okay, great. Olutomi, are you with me too? So moving on, phase two, knowledge extraction. Now that we have discovered the knowledge, explore, identify, establish, we now have a kind of formal, should I say formal um, understanding of the relationships in the data. It's now time to extract the valuable information. So we are not extracting all the information that there is in the data. We are not extracting just the ones that are very useful for our purpose. So we go to the extract phase. Here we can assemble the target data from the knowledge discovery phase. So we kind of gather them together. We we see if they are large enough to contain useful patterns. So not all patterns in the data are useful. There's some patterns that we can find in data, but they may not be useful for the kind of problem we want to solve. You understand? So we want to see whether the patterns we have are large enough, whether they're consistent throughout the data, right? And whether they are not that they're concise to be marked, which means um, I mean some databases are very big. So if you want to extract all the data from a database, or maybe all the useful data from the database, sometimes it may not be very practical because it may be too big for us to extract using our traditional tools, right? Even if we begin to use big data tools that can process big data like voluminous data, right? It might be too cost intensive, or it might be outside what we really want. So typically, we want to be able to understand, in the extract phase, we want to be able to understand whether the data that we have, that is the useful knowledge we have, is concise enough to be mined, right? We want to see whether it's large enough to contain the patterns that we really need, because what we have been trying to do so far was to discover the patterns. So now it's time to extract those patterns as knowledge, and so we want to make sure that it's concise enough to be mined. Once we extract them now, we begin to transform them. So this is where you begin to do a lot of data processing, data transformation. We can smooth the data where we eliminate noise. When we talk about noise in data, we're talking about information that are not so relevant for the data, right? Information that, even though they are part of the data, they are not really relevant in terms of the value that they can provide. Which means if we drop those pieces of data, or those portions of the data, right, we'll be ending up with the remaining data we're ending up with will be very valuable for the problem we're trying to solve. But in their presence, the presence of these guys can kind of um, can 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 cause a kind of impurity for our data, can damp the value that we can get from that data. So when we implement smoothing, it's a transformation technique that kind of allows us to fetch out um, to eliminate any kind of random noisy data that is not really going to be useful for us, and just really end um, with signal. So we talk about signal, we talk about noise. So signal is a part of the data that is really providing informative value for us. So we can do aggregation. Aggregation is like we just really get summary information. It could be statistics like mean, median, mode, kurtosis. We kind of understand the distribution of the data. So to aggregate now is like we want to now get a kind of singular value that summarizes what we really have in the data. So it could be the count of the data, that's the number of elements we have in the data, the length of the data frame, or the data set, the size, the shape, things like that. Normalization is like, okay, we want to now kind of scale the data to a certain range. Let's say the data we have, or the data we're able to extract now, let's say we've been able to convert all that data now to numerical data, right? And in our numerical data, we have values ranging from 1 to 1000. So maybe a particular column has like one values within the range of 1 to 1000. Then another one kind of has values within the range of 1 to 30. Another one 1 to 10, right? Um, we really want all the columns to kind of fall within the same range. So we'll just implement a kind of normalization technique so that all the data now we can now kind of compress them to a certain specific range, maybe 1 to 10, so that consistently all the columns will be showing 1 to 10, and that is not going to really help us. Um, that's going to make that data very useful for the purpose we're trying to achieve. Then we do feature engineering. Feature engineering is not like trying to kind of engineer the columns, the input features in the data. We begin to we can reconstruct new columns from existing columns. We can even reduce columns from all that. We just really try to fit the columns to shape um, in order to end up with features or columns that are going to be very useful for what we're trying to solve. When we are done with all these very um, fancy techniques now, we end up getting something that we can now use, right? So this brings us to phase three, which is advanced analytics. And these steps, pretty much what we're doing here is just to simply apply the extracted knowledge. And remember what I mentioned earlier, that this knowledge now that we've extracted will serve as inputs to further processes. So we're trying to apply this extracted knowledge to other things like predictive modeling. In the predict, right, the decisions to take. Hello. Okay. So um, we are trying to now use the extracted knowledge for further purposes. Like decision analytics now wants to be able to get the best decision to make, maybe about who to vote for. So we can now make recommendations based on those models and say, based on the data, from the data that we have, this looks like the best candidate to vote for in the elections. We can also do visual analytics where we now kind of create visualizations using the information. So let's say you want to present your discoveries now to a non-technical audience, maybe your manager or senior leadership or stakeholders, right? You will not be using a lot of technical language. So you want to now kind of summarize all the knowledge and information you have gotten in a kind of dashboard or visualization, right? So we call this visual analytics, where your goal is to create visualizations using information. So in those visualizations, everybody will be able to see the patterns in the data, in a relatable way, in a way that they can interpret. Be able to see the clusters or groupings in the data in a way they can interpret, and a non-technical user will be able to make sense of that information. So once you are done with this step now, that is the end of your data mining step, and I think that's pretty much the end of lecture on data mining. So let me now move to questions. If you have questions concerning or regarding what we have done so far, I would also ask questions, so get ready. So does anyone have any questions? If you have, let me know what the questions are based on what we've looked at so far.
I don't.
Okay. Okay. In that case, I guess I would have to now be the one to ask questions. So let's go back to this slide on data mining, right? So we have 6 steps: explore, identify, establish, extract, transform, and use, right? So I've already broken this down into 3 phases. So tell me, um, explore, identify, and establish. Which phase, from what you have looked at already, which phase do they fall into?
Phase one.
The phase one, the knowledge discovery.
Okay, great. Knowledge discovery. So, Mr. Ken, you're next. For extract and transform, which phase do they fall into?
Phase two, knowledge extraction.
Okay, very good. Then what about the final one, which is use? What phase do they fall into? Does it fall into?
Advanced analytics.
Okay,
Yeah.
great. So advanced analytics. So that's pretty much it. For phase one is the knowledge discovery phase. So we are trying to, you know, get the insight from that data. Then phase two, we're trying to now extract what we've discovered, and then phase three, use. Now let me now go back to something I mentioned much earlier in the lecture. Let me go back to that. Now, when we use the term data mining, right? What are we really mining? What are we really mining? Are we mining the data, or what exactly are we mining?
Knowledge is we are mining knowledge to get insights, which is knowledge actually.
Okay, okay, okay. Second, do you agree with that?
Yeah, that was where you mentioned the KDD.
Okay, great. So that's
Yeah.
that's it. It's good you remember that KDD, knowledge discovery in databases. So
Data.
what we are doing now is to mine knowledge, and in order to mine knowledge, first of all, we have to discover the knowledge, right? I mean, it's like it just really takes an analogy from mining mineral resources. We want to mine gold. We don't just start digging everywhere, right? We begin with exploring. So we begin by discovering where the gold actually is. So we explore to find which portions of the subsurface structure of the earth do we really have this gold. When we have discovered that, we now begin to extract it. When we have extracted that, now because it's in its raw form, we cannot just be immediately use that. We have to transform it. I hope you can see the way data mining followed the analogy. I like the way the pioneers of data mining created these steps, because they kind of pretty much followed an already established um, discipline, like the process in an already established discipline, in the engineering discipline. They kind of follow that procedure. For example, petroleum resources. When you want to mine, um, when you want to mine what's it called, oil and all that. First of all, wants to discover where the oil is. When you have discovered, find what is the um, underneath the ground, and then establishing that there's really oil here, right? Then you go ahead to extract it. When you're done extracting it, we cannot begin to use that oil. That oil has to be transformed. So it is transported, to be distilled into the various fuels that we now have, petroleum, um, sorry, not petroleum, petrol, kerosene, what's it called? Even the solid fuels that we have, they kind of distill it into those various components. And at the end of the day, you now have something that the everyday user now can use. So you see that they kind of systematically followed an already established procedure in the engineering field, and it really makes a lot of sense because now we can use this methodology now to get a lot of meaningful value, meaningful insights, and um, valuable outcomes from the procedure when applying it for working with data. So that's pretty much it. Okay, I think I should ask one more question. One more question before we round up. Um, Let me see. Okay. All right. I think I should ask a question from here. So remember, I gave an example, another example, apart from the political example. I gave an example with students in a university, and then we talked about trying to find the relationships between attending the library, reading at the library, and passing the exams, right? And we already see that if the percentage of people who fail the exams after attending library, if it's so much, then we will not call that an if-then pattern or relationship, right? But if it's little, if it's so little that it's almost negligible, based on the confidence interval we choose. For example, if we choose 99% as a confidence interval, right, it means we need to have at most 1% of the data failing. If we choose 95% as confidence interval, that means at most we must have 5%. If we have more than 5%, we will not consider it as an if-then pattern. But if we have 5% or less, then we can still say it's an if-then pattern. That is, if people attend the library, then they pass the course. Which means the remaining 4% or 5% that did not pass the course were probably outliers. Maybe some other things went wrong. So we might want to look at other areas like was there some kind of health conditions, right? Were there other things that could have influenced the performance of the exams? So that makes us now examine other possible conditions or scenarios, right? Now, for this example, for people who are outliers in this relationship between attending the library and passing the exam, right? For people who are outliers, what um what what's it called? How do I watch this question? What are the various conditions you would likely you would think about for cases where we have like 4 or 5% of students not passing the course despite attending or despite going to the libraries to read? So can you guys come up with some sort of examples? Because what I just really want to do now is to help us kind of reason about some of these ideas so that we can begin to think like data scientists. So um, now I want you guys to come up with examples of conditions, possible conditions that could have reason that prevented these 5% or less people to fail the course that the rest of the 95% of people who attended libraries passed. So what conditions could have made them fail the course? So let's just come up with possible conditions or cases. So who do I start with?
Uh, what if it's possible that even though they attended the library, they they were sleeping instead of reading?
Okay. Yeah, that's a good one. Yeah, that's actually
They
very
are,
possible. Yeah, go ahead.
uh, then maybe even if they attended the library, read, unfortunately on the day of the exam they were absent, they will still fail the course.
Exactly.
So at least those are two conditions that it doesn't match the if then pattern. So
Exactly. So
Yeah, also possibly they did not finish the exam. I don't know. Yeah. So they were not able to complete. Maybe they didn't complete within the allotted time.
Okay. Yeah, yeah,
Yeah,
that also makes sense because I mean, if you want to, if you are looking for examples of people that will fall within a 95% of people who pass the course, right? You must be able to look um for similar consistent patterns with these guys. So if these 5% of people now, right, if some of these conditions, are coming up, like, not going for the exams, or you went for the exams, you didn't pass the exams, you know and things like this are happening. I mean, sorry, you didn't complete the exams, not pass, you didn't complete the exams. I mean, when I was in school, there was this interesting case of people wanting to compete as to who comes out of the exam first. I don't know if you guys remember such scenarios. There are people
yeah,
who they just really want to jump out of the exams. And guess what? When the guys stand up and go to submit, everybody looks at them with so much, oh, yeah, this is so impressive. You mean you are done with this exam? And it's like everyone is trying to hail them and say, hey, I don't scatter. But he has done nothing. He has not
yeah. It
completed it.
doesn't really mean they knew what they wrote.
You understand?
It's possible too.
So that's it. Whereas there's some other persons, the thing is that, there's really no, what's it called? There's no one hard and fast rule for this. There's some persons that would sit in the exam and be the very last persons to finish, right? And you will think that they have smashed, they have written all there is to write, even collect extra sheet and still fail. You see? So, I mean, there's this slang that, as Nigerians we're all familiar with. People will say that extra sheet not be first class. So you may collect extra sheet, but
Yeah,
that doesn't mean that you have
like
really
pass.
delivered. Yeah, you see. So, so many conditions. And that's why in data mining, we analyze a lot of things, because the truth is that, you know, patterns are not usually consistent. You understand? So, not everybody who passed had consistent conditions that made them pass. How about people who pass after doing some shady things like sorting and things like that? You know, how about people who pass by, bringing, what's it called, bringing exhibits to the exam and not getting caught. So many things like this. I mean, obviously, if you have passed through a Nigerian system, you'd even know these are not new things. You have situations of people who consistently maintain high grades in school, but close people to them know that these ones na scam. We just know that, yes, there are 4 pointers that are doing well, but there are some shady things that I've been doing. I mean, you will see cases of people being experts in cheating at the exam. And you just wonder, how did these people do it? How do you guys do this without getting caught? The day you want to attempt something like that and say, okay, let me even try, they will catch you that day. Then you will regret and say, okay, I'm not doing this again. So there are cases like that. Not everybody who passes now really, not everybody who passes the course now really follow the same conditions. So that tells you that, there are so many things to check for. That's why we check a lot of patterns. So that's why in association rules, when checking association rules, we're not just checking a single pattern. We're checking so many patterns and trying to see from what information has been given in our data, what are the various conditions that lead to the observations that have been made in the data. What are the underlying on and non-obvious patterns that cause the observations to emerge, right? What are the hidden things that we can discover? You understand? There's a general term we call pattern discovery. In data science, I don't know if you guys have heard of that term. It's pattern discovery. It's a term called pattern discovery, and it's pretty much similar to knowledge discovery in data mining. But pattern discovery was a term that kind of became um, a very central idea in data science, right? So, what pattern discovery does is that there are two types of pattern discovery. There's the case of trying to discover obvious patterns in the data. You understand? For example, when you want to check, okay, students in the university who attend tutorials outside lecture hours, right? What are the grades they have? That's different from the case of whether they pass or not. We want to now see their grades, so we know that they have passed. So we're taking the data of people who passed now, and we're trying to check whether from this data of people who passed, we want to see for those who attended tutorials outside lecture hours, We want to see the pass rate. We want to see how many of them, I mean, how much they passed. I mean, not the pass rate. The pass rate is like checking the ratio of pass versus fail. In this data now, we don't have people who failed. We only have people who passed, and we're interested in knowing the scores. So that kind of gives you a kind of regression problem where we're trying to get the direct relationship. It's an obvious pattern, right? These persons that attended the tutorials, this is the obvious score. So pattern discovery, one of the categories of pattern discovery is to discover these obvious patterns, right? Then there's another category of pattern discovery where we're trying to discover not obvious patterns now, but discover some hidden patterns. So, for example, some of the examples we have talked about earlier, like um, students passing the courses and the various things that could have caused that. Those things that could have caused a student to pass or to not pass, even after fulfilling some conditions, right? Some obvious conditions. There's some other things that could still make the student not to pass. Those things are not obvious. So the goal of pattern discovery in this particular category of pattern discovery now is to discover the hidden patterns, the patterns that are not obvious, but it's these not obvious patterns now that lead to the observed outcomes in the data. Do you understand?
Yes.
So
Yes.
it's a very rich field. There's an analogy I created whenever I'm explaining pattern discovery. There's an analogy I created to kind of simplify it. So let me give you guys the analogy, right? It's something I called the two-room analogy. Two room. So there are two rooms, right? One room is a dark room. The other room is a lighted room. It has light. Now,
Okay.
yeah. Now in the lighted room, right? You enter that room. Your goal is to be able to look at the obvious patterns. The obvious patterns are the things that you can see, all the objects in that room, and to be able to now identify what the name of those objects are. That's a kind of pattern discovery, right? And the pattern discovery in this sense, we can call it classification because what you want to do now is to be able to classify the objects that you see. What is the name of this object? What class or category do they fall into? You understand? So it's a very obvious pattern discovery. So you don't need to get this stress. All you just need to do is to map, you know, what you're seeing, right, to the information about the object. So when you see a particular object, you already have insight in your head. You already have the answer for that. So you simply map what you have seen to the interpretation for what you're seeing, and that gives you the answer. So okay, this is an office chair. These are what's it called? Relaxation objects. This is a bar. This is a that. You're able to map that. The case is different when you go to the dark room. In the dark room now, because you cannot see what is in the room, but you know that there are objects there, right? Your goal is not to immediately start naming the objects there because you can't see them. So you cannot map the visual information that you are not seeing. You cannot map the visual information to the answer in your head, the interpretation in your head. You don't know it. So what do? You begin to look for hidden patterns, the hidden structure of the room, right? You begin to look for the hidden structure. So what you do to achieve that now is to dig into the darkness. You now grope into the darkness to be able to. I mean, you begin to touch objects. You begin to touch various things in the room, right? And as you're touching those things, your brain begins to do a lot of analysis, interpretation. Okay, this object, it looks like, okay, this is a wooden object. This must be a table. You check all the corners, you check all the edges and all that. So once you get as much information as you can get, right, you're able to now really know the hidden structure, all right, about those objects, and then you can now make sense of it. So pretty much what you have done now is to, grope in the darkness to identify, or should I say, to discover knowledge. In the littered room, we're not discovering knowledge because the knowledge was just obvious. It was just like map this one to the answer, map this one to the answer. Right? It's an obvious pattern that has led to the observations. But in the dark room, right, the patterns are not obvious because the environment is dark. So you have to discover the insights about that room, and the insights are hidden insights. You have to be able to discover the hidden knowledge from that. So most times, this is the kind of pattern discovery we call knowledge discovery. And what you do most times in knowledge discovery are things like clustering, dependence modeling, association rule mining, and some of these techniques that we have looked at in this knowledge discovery phase. These are the things that you use in this aspect of pattern discovery. And we do that a lot in data science, even in machine learning. We use all these techniques now to make meaningful sense out of data. Does it make sense?
Okay.
Okay, so do you have any questions before we round up? We spent
I
quite a
just
bit
wanted to
time.
ask, like in association rules, if-then
Okay,
pattern,
okay.
for the confidence level, so will you be the one to choose what your confidence level will be, or is
Mm,
there?
sometimes
Yeah.
you can choose based on like kind of domain understanding. So um, most times, depending on the problem you're solving, there's always a baseline, like a generally accepted baseline in that industry. If you're solving a problem within the education industry, maybe trying to understand students, student performance, right? The university system may have like a baseline, a statistical baseline. So you can use that to kind of choose a confidence interval. Sometimes people choose, I mean, sometimes the baseline is like 99% confidence interval. Sometimes it's 99.5%. Sometimes it's even as high as 99.9%, which means the people who don't follow this if then pattern should just be as highest 0.01%. That I mean highest 0.01%, yeah, 0.01%, meaning that if you just have as little as that as your confidence, I mean as your counter examples, then we can still confidently say it's a consistent pattern. But if they exceed that ratio of the counter example, then we say that it doesn't hold. So the moment your counter examples is making this actual successful patterns fall below the confidence interval that you have chosen. Maybe if you choose 99%, if it's not falling below 99%, right, you realize that we can't really call this a consistent pattern, so we have to now discard that pattern. So yeah, it really depends on the industry they decide. Most times there are baselines for that. And then if they are not baselines, sometimes as a data scientist, you cannot use experience and sound judgment now to kind of decide what confidence interval to make. And sometimes even, you can still do a lot of statistics or mathematical analysis to determine which exact percentage you should choose. So there's not really hard and fast rule. We can have different values, but most times the minimum confidence level that we have is 95% most times.
Okay.
Yeah.
Okay. All right. Thank you.
All right. You're welcome. All right, everyone. So I hope you enjoyed tonight's session. It's a good way to round up this module before we now start the practical sessions. So I hope you've enjoyed what we've looked at tonight.
Yes.
Yeah.
Yes.
Okay, great.
Yeah.
All right, everyone. So we'll be rounding up here. Enjoy the rest of the night.
All right. Thanks.